Assalamualaikum warahmatullahi wabarakatuh and hi, we are from Group 2 want to present the titanium trichloride as catalyst. First of all, the introduction of titanium trichloride. What is titanium trichloride? Titanium trichloride is the inorganic compound with the formula TiCl3. Titanium trichloride is one of the most common halides of titanium. It is also an important catalyst for the manufacture of polyolefins. What is polyolefins? Polyolefins is a type of polymer produced from a simple olefins that also called an alkyne as a monomer. Next, the properties of titanium trichloride. The molar mass of titanium trichloride is 154.225 G per mole. The appearance is red violet crystals. The density is 2.64 G per cm cubic. The melting point of titanium trichloride is 425 Celsius and the boiling point of titanium trichloride is 960 Celsius. Titanium trichloride is very soluble in acetone, acetonitrile and certain amines, and also insoluble in ester and hydrocarbons. Next, the structure and bonding of titanium trichloride. Each titanium atom has one d electron, rendering its derivative paramagnetic, that attracted into a magnetic field. The solution of titanium trichloride are violet, which arises from excitations of the electron. The color is not very intense since the transition is forbidden by the Laporte selection rule. Laporte selection rule is a spectroscopic selection rule that only applies to centrosymmetric molecules and atoms. For solids of titanium trichloride known as polymorphs. Polymorphism is the ability of solid material to exist in more than one form or crystal structure. All feature titanium in an octahedral coordination sphere. These forms can be distinguished by crystallography to see crystal structure as well as by their magnetic properties, which probes exchange interactions. Beta titanium trichloride crystallizes as brown needles. Its structure consists of chains of titanium Cl6 octahedral that share opposite faces that the closest titanium contact is 2.91 angstroms. This short distance indicates strong metal-metal interactions. The three violet layered forms, named for their color and their tendency to flake, are called alpha, gamma, and delta. In alpha titanium trichloride, the chloride and ions are hexagonal close-packed. In gamma titanium trichloride, the chlorides and ions are cubic close-packed. Finally, disorder in shift successions causes an intermediate between alpha and gamma structures called the delta form. The titanium Cl6 share edges in each form with 3.6 angstrom, being the shortest distance between the titanium cations. The first diagram is the alpha titanium trichloride. The middle the diagram is the beta titanium trichloride, and the right diagram is the gamma titanium trichloride.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Izaya Yasmin Zulaika binti Hashimi and my matric number is AS11594. Today I would like to teach about synthesis and reactivity of titanium trichloride. So let's go. Okay, synthesis and reactivity. Titanium trichloride is produced usually by reduction of titanium tetrachloride. Older reduction methods use hydrogen. Okay, so this is the formula equation, and it is conveniently reduced with aluminium and sold as a mixture with aluminium trichloride. Okay, and then the complex adopts a meridional structure. Alright, next, titanium trichloride forms a variety of coordination complexes, most of which are octahedral. Okay? Yeah. Alright. And then this is the formula equation. Okay. The more reduced titanium 2 chloride is prepared by the thermal disproportionation of titanium trichloride at 500 degrees Celsius. The reaction is driven by the loss of volatile titanium tetrachloride. Okay. And this is the formula equation. Alright, application. Titanium trichloride is the main Ziegler-Natta catalyst, responsible for most industrial production of polyethylene. Okay, and then the catalytic activities depend strongly on the polymer of the titanium trichloride and the method of preparation. Okay, here's the point. Ziegler-Natta catalyst, and then polyethylene, and then this one, and the method of preparation. Okay, alright, this is the simple application. Polyethylene is a linear man-made man-made polymer primarily used for packaging. Okay, for example, ethylene became polyethylene. Alright, for laboratory use, titanium trichloride is also a specialized reagent. Alright, it is a specialized reagent in organic synthesis, useful for reductive coupling reactions. Okay, useful for reductive coupling reaction, often in the presence of added reducing agents such as zinc. Okay, it reduces oxidants to imines. Okay. Oxidants to imines. And then titanium trichloride can reduce nitrate to ammonium ion, thereby allowing for the sequential analysis of nitrate and ammonia. And last one, slow deterioration occurs in air-exposed titanium trichloride, often resulting in erratic results, for example, in reductive coupling reactions. Okay, for safety. Alright, for safety, first, titanium trichloride and most of its complexes are typically handled under air-free conditions to prevent reaction with oxygen and moisture. Okay, and then the second one, depending on the method for its preparation, samples of titanium trichloride can be relatively stable and pyrophoric. Okay, that's all for safety. So that's all from me. Thank you.
Now let us look at the Ziegler-Natta catalyst. First, what is Ziegler-Natta catalyst? A Ziegler-Natta catalyst is a catalyst named after Carl Ziegler and Uriel Natta. It's a catalyst used in the synthesis of polymers of 1-alkenes. Ziegler-Natta catalysts, any of an important class of mixtures of chemical compounds remarkable for their ability to effect the polymerization of olefins to polymers of high molecular weight and highly ordered, which is stereoregular structures. There are two broad classes of Ziegler-Natta catalysts. First is heterogeneous catalysts. Heterogeneous supporter catalysts based on titanium compounds are used in polymerization reactions in combination with core catalysts, organoaluminum compounds such as triethyl aluminum. This class of catalysts dominates the industry. Second is homogeneous catalysts. Homogeneous catalysts usually based on complexes of titanium, zirconium, or hydrogen fluorine. They are usually used in combination with a different organoaluminum co-catalyst, metalluminooxane or metalluminooxane. These catalysts traditionally contain metal oxines, but also feature multidentate oxygen and nitrogen-based reagents. This is the diagram of a post-metal-oxine catalyst developed at Dow Chemical. Ziegler-Natta catalysts are used to polymerize terminal alkenes. Example is ethylenes and alkenes with the Wien-Veer double bond. Stereochemistry of poly-1-alkenes is an example reaction that uses the Ziegler-Natta catalyst. Natta first used polymerization catalysts based on titanium chloride to polymerize propylenes and other 1-alkenes. The short segments of polypropylene showing example of isostatic and syntactic tacticity. The concept of stereoregularity in polymer chains is illustrated in the picture on the left with polypropylene. Stereoregular poly-1-alkene can be isostatic or syntactic depending on the relative orientation of the alkyl groups in polymer chains consisting of units, like the CH3 groups in the figure. In the figure. In the isostatic polymers, all stereogenic centers CHR share the same configuration. The stereogenic centers in syntactic polymers alternate their relative configuration. Both isostatic and syntactic polypropylenes are crystalline, whereas atactic polypropylene, which can also be prepared with special Ziegler-Natta catalyst, is amorphous. Now let us look at commercial polymers prepared with Ziegler-Natta catalyst. As example, we have polyethylenes, polypropylenes, copolymers of ethylenes and 1-alkenes, polybutene-1s, polymethylpentanes, and so on. Yeah, that's all for me. Thank you.
I'm going to continue with mechanism of Ziegler-Natta catalytic polymerization. As you can see, there are 4 steps here. The first step is the activation of Ziegler-Natta catalyst. The second step is the initiation step, while the third step is a propagation step, and the last step is a termination step. Activation of Ziegler-Natta catalyst. Herein, titanium tetrachloride and the triethyl aluminum catalyst system is taken as an example. The titanium tetrachloride compound has a crystal structure in which each titanium atom is surrounded by 6 chlorine atoms. On the crystal surface, a titanium atom is surrounded by 5 chlorine atoms with 1 empty orbitals to be filled. When the triethyl aluminum comes in, it donates an ethyl group to titanium atoms, and the aluminum atom is coordinated to one of the chlorine atoms. Meanwhile, 1 chlorine atom from titanium is kicked up during this process. Thus, the catalyst system still has an empty orbitals as shown in the figure 5. The catalyst is activated by the coordination of triethyl aluminum to titanium atom. Figure 5 shows the activation of Zn catalyst system by coordination of triethyl aluminum to titanium atom. Second step, initiation step. The polymerization reaction is initiated by forming alkene metal complex. When a wine monomers like propylene comes to the active metal center, it can be coordinated to titanium atom by overlapping their orbitals. As shown in figure 6, there is an empty dxy orbitals and a filled dx2 y2 orbitals in titanium outermost shell, while the other four orbitals are not shown here. The carbon-carbon double bond of alkene has pi bond, which consists of filled pi bonding orbitals and an empty pi anti-bonding orbital. So the alkene pi bonding orbitals and titanium, the xy orbital, comes together and share a pair of electrons. Once they are together, the titanium, the x2, y2 orbitals comes mighty close to the pi anti-bonding orbitals, sharing another pair of electrons. Figure 6 shows the molecular orbitals representation of monomer coordinating to the metal center. The formed alkene metal complex like this then goes through the electron shuffling, with several pairs of electrons shifting their positions. The electron pairs from the carbon-carbon pi bond shift to form titanium-carbon bond, while the electron pairs from the bond between titanium and triethyl aluminium ethyl groups shift to form a bond between the ethyl group and the methyl substituted carbon of propylene, as shown in figure 7. After electron shuffling, titanium is back with an empty orbital again, needing electrons to fill in. Like structure 2. Figure 7 shows the formation process of alkene metal complex. The next step is propagation step. Propagation step. When other propylene molecules comes in, this process starts over and over again, giving linear polypropylene, as shown in Figure 8. Figure 8 shows the propagation towards the polymeric change. And the last step is termination step. Termination is the final step of a chain growth polymerization, forming dead polymers, which is the desired products. Figure 9 illustrates several termination approach developed with the aid of core catalyst triethyl aluminium. Figure 9 illustrate 3 termination approach. The first one is beta elimination from the polymer change forming metal hydride, and the second is the beta elimination with hydrogen transfer to monomer, and the last approach is hydrogenation. That's all. Thank you for listening.